This is the video for pre-lecture 7. In the previous lectures, we've introduced the concept of the explicit and implicit Euler's method. And these are both examples of a first-order method where we get that first order from our global error, and we found that the error for both our explicit and implicit were order delta t, meaning that if we want to increase our precision or our accuracy by a factor of 2, we have to cut the time step by a factor of 2, so increase the number of time steps we're going to take by a factor of 2. And while this is certainly something that can be used to get whatever precision that we're looking for, it's not necessarily the most efficient way. And so this is also what we would refer to as a one-step method, where to take each mapping from state xn to state xn plus 1, we perform one evaluation of the slope. And so while this is easy to implement, the convergence properties are not ideal. The Runge-Kutta family of methods is a multi-step method with variable order depending on the number of steps taken. And so actually the explicit and implicit Euler methods are part of the family of the RK scheme, but they're only a one-step version. We're going to look at the multi-step version. So the generic or the general RK equation is just simply xn plus 1 is equal to xn plus delta t times some slope approximation k. And so that k value is a weighted average of the different step evaluations or different slope evaluations that we're going to make in our method. For the explicit Euler, if we simply say that our slope approximation k1 is equal to the function evaluated at state xn and time tn, and set our slope k to that k1 value, that would be an example of a Runge-Kutta one-step method. But we want to think about what happens if we want to take multiple steps to improve the accuracy of the approach. So we're going to discuss first the two-step method. So given an ODE, dx dt is equal to f of x and t. The generic general RK equation is xn plus 1 is equal to xn plus delta t times k. The first of our two steps that we're going to take is we're going to evaluate the slope at our current state. So at our current state, xn and tn, that's going to correspond to this red dot here. We're going to calculate the slope using that function f to make our approximation for our k1 value. And so this line segment here in red corresponds to our slope k1. Now for the explicit scheme, we would normally just take this slope approximation and take a full time step going from 0 to 1. But for the RK2 method, we're going to take a half time step. And so what we're going to do is we're going to go from 0 to delta t by 2. But we're going to move along the slope calculated at that xn tn state. So we have this red dashed line, which is parallel to the red solid line, and that takes us to this point here, which we're going to label as x sub h and t sub h, corresponding to the half step position. Well, what are those values? Well, x sub h, you could imagine, is simply taking sort of a half Eulerian step. So we started at xn plus, instead of delta t, it's now delta t by 2 at the slope angle k1. And of course our th is going to just simply be our current time tn plus a half step delta t by 2. So now that we've calculated our half step state, we can use those values to calculate a slope approximation, k2, at this position. And so that's what we have in green. This is our k2 approximation. So now we could determine k as some weighted average of k1 and k2, but it turns out that the most accurate approach is to simply let k equal k2. And so then to take a full step to perform the mapping from xn to xn plus 1, we say that xn plus 1 is equal to our current state, xn, plus a full time step delta t times our weighted slope approximation k, which in this case is just going to be k2. So graphically, this takes us back to our xntn state at our red dot, but now we're moving a full time step from 0 to 1 at a slope angle of k2. To take the next mapping, we would repeat the process. So to go from state xn to state xn plus 1, we had to calculate our slope approximation twice to get our k1 value at our current state and our k2 value at our half-step state. So let's go ahead and do an example. So we have an example of dx dt is equal to minus 2xt. We have an initial condition at x at t equals 0 is equal to 1. And we have an analytic solution, which is just the exponential of minus t squared. So we would go through our process again. We'd say, okay, what's our current state? What's our half-step state? At both states, we're going to need to calculate a slope approximation, and then use that to get a full step approximation. So let's work through the process. So what's our current state? So our current state, sort of step 0, is that xn is equal to 1 and tn is equal to 0. We're going to go ahead and let delta t equal to a half. Okay, we have to calculate our first slope approximation, so k1 is equal to f of xn equals to 1 and tn equals to 0 is going to be equal to minus 2 times the x value, so that would be 1, times the t value would be 0, gives us a k1 value of 0. Okay, so now we have to calculate the state for the second slope approximation. So this would be our half step state. So we need to get our x sub h value, which is equal to xn plus delta t by 2 times k1, which is going to just be 1 plus 1/4 times 0 is equal to 1, and th will just be equal to tn plus delta t by 2, which is equal to 1/4. So now we have our half-step state. We can perform our second slope approximation, so that would be k2 is equal to f of x sub h and t sub h. So it's going to be minus 2 times 1 times 1/4, where the 1 comes from our x sub h and our quarter comes from our t sub h. So that's going to be equal to minus 1/2. Calculate the weighted slope average is very simple because we just say k is equal to k2, which then would be equal to minus 1/2. Now we need to perform our full step, which would be xn plus 1 is equal to xn plus delta t times k, which in our case is going to be 1 for our initial state plus the full time step 1/2 times our k value, which is equal to minus 1/2. So that would give us a value of 3/4. Okay, let's take another step. So for our second step, our second mapping, our xn value is going to be equal to 3/4, and our tn value is going to be equal to 1/2. Our k1 is going to be equal to minus 2 times our x value, which is going to be 3/4, times our t value, which is going to be 1/2. And so that's going to give us a slope approximation k1 equal to minus 3/4. Okay, so we can use that slope approximation to get our half-step state, so that'd be x sub h equals our current state, which is 3/4, plus a half-time step, which would be delta t by 2 is 1/4, times our slope approximation, which would be minus 3/4. So it would be 3/4 minus 3/16. So that would be equal to 3/16. Our t sub h value is going to be just simply a half plus a quarter would be 3/4. Sorry, this is not 3/16. This should be 9/16. Because it should be 3/4 becomes 9/12 minus, or 3/4 becomes 9/16, 12/16 minus 3/16 would be 9/16. Okay, our K2 value then would just be equal to minus 2 times our x at our half step state would be 9/16 times our t at our half steps would be 3/4. And so that's going to give us a value of minus 27 over 32. And so again, our K value then would just be minus 27 over 32. And then our full step would be xn plus 1 is equal to the current state, which is 3/4, plus a full time step, which would be a half, at our slope angle, which would be minus 27 over 32. Okay,